Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So the other important aspect which we have to know about the single crystal plastic deformation is work hardening behavior. So what is this work hardening? We have now seen that um, in a, as I just mentioned in the beginning, I mean few lectures back, when we talk about crystalline plastic deformation, the plasticity is always considered as dislocation mediated plasticity, right? So we have also seen several dislocation characteristics in terms of generation, interaction, multiplication, okay, intersections, and dislocation reaction, and so on. So all those concepts will come in handy here when we talk about work hardening. Okay, so what is that? I'm showing some interesting plot, right? That stress versus strain. Basically, this is a critical resolved shear stress versus shear strain plot of a single crystal. Okay, let us look at that graph. I mean, plot a little more closely. It conveys a lot of information. So we have to be very careful in looking at this and then try to understand. This is most fundamental idea. Okay, so what does it say? This plot shows something called stage 1 as the strain increases in the beginning, and then there is a steep increase in the stress, and then after that it starts slowly coming down. So again it has got about three stages. Okay, the stage 1, stage 2, and then stage 3. Okay, so stage 1, okay, it is basically a low work hardening rate. That means we will see that the dislocation activity is the rate of dislocation interaction, and the activity is low, and except that a little hardness is changing in the material. And the moment it start going to the stage 2, excuse me, the moment it goes to stage 2, you can see that the stress increases significantly due to multiple slips. Okay, and then it goes on, and then after some time, the moment we start the stage 3, it starts slowing down, and then you can see that in the stage 2, the increasing high constant work hardening rate. The work hardening rate significantly increases, and after some time it is staying constant, and then after that it slows down. So in this, if you extend this straight line, then you appreciate that how much the decrease in the work hardening rate, you can see that is given by this dashed line. Similarly, the increase in the work hardening rate is also given by this arrow hashed line. Beautifully, it illustrates the how the work hardening rate increases and then decreases. Okay, so now we have to just understand in a single crystal why this happens, and how do we understand. This is a very basic and important fundamental idea which you have to keep in mind to I mean extrapolate these ideas to polycrystalline deformation or any other polycrystalline you know deformation mechanisms and so on. So the low hardening rate at stage 1, the deformation is associated with the fact that there is an absence of dislocation intersections. Okay, so this is belong to this region. So what does it mean is the key factor to note is increase in dislocation density and long fine slip lines and low strain hardening rate and few dislocation intersections. So we have seen that in the dislocation dynamics earlier or dislocation mechanics, unless the dislocation interact and then makes the intersections, the formation of little harder dislocation structures like kink or jog and voids and other things are all not going to happen, which are all the hard particles. I mean, will act as a hard particle. They are not going to happen. Okay, so that means they are all the signatures of high rate of dislocation interaction, which is not taking place in the stage 1. The high strain hardening rate in the stage 2 is the result of intersection and trapping of dislocation within the crystal. So now we are talking about intersection. That means the dislocation start interacting with each other. That means after the initial glide, that means the dislocation start gliding in a glide plane without any hindrance, and as the strain goes up, the number of dislocation increases, that number of dislocations per unit area increases, and then as a result, now intersection start happening. So the primary signatures of the stage 2 is dislocation multiplication, activation of new slip systems, formation of sessile and non-moving slip planes, increase in strain and internal stress. You see, these descriptives are very, very important. As you move to a second stage of work hardening rate, you see the complete contrast in the dislocation and microstructural features. If you look at the stage 3, the decreasing strain hardening rate is a result of dynamic recovery process occurring simultaneously with the strain hardening. So you see, you have to now remember a strain hardening and then strain softening. We can say that opposite word. Okay, there is another word we can use. Is a dynamic recovery also will act as a strain softening mechanisms. You can consider it like that to start with. We will give more importance to all this terminology, and we'll get into details as we proceed in the course. But then it is easy to remember. Strain hardening taking place. So that means it is getting reduced. That means what? Something opposite to happen. That is strain softening. Okay. So here we can consider the dynamic recovery. Okay, is opposite to strain hardening. So that is happening in the stage 3. So what are the primary or key signatures here? Creation of jogs, point defects, long and narrow dislocation loops. So you know now what is a jog. You know what is a point defect or vacancy, how it is getting generated. Okay, interstitials, how it forms. All these descriptors you have some idea. We have already seen in terms of dislocation reactions. So the dislocation loops and cross slip, you know, screw dislocation. Okay, the screw dislocations only can undergo this kind of mechanisms. That means it can easily surpass the obstacles through these mechanisms. Okay, and recombination of partials due to high stresses. So the stage 3 again shows very significant and very different signatures as compared to stage 2 in terms of dislocation behavior. Okay, so the entire stress strain curve for a BCC crystal resembles stage 3 deformation in FCC crystals. So please understand this single crystal deformation behavior, what we have seen so far, stage 1, stage 2, stage 3 is for face-centered cubic crystal system. Okay, and for a BCC, body-centered cubic crystal system, the entire curve will look like a stage 3 only. Okay, so that means you have very different kind of work hardening behavior will be exhibited by materials which has BCC crystal system, and these kind of work hardening behavior will be exhibited by materials which shows or which has FCC crystal system. Very important, basic understanding. So I just use the word dynamic recovery suddenly. Okay, what is recovery? Let us first see that, because we are now denoting the whole area as a decrease due to recovery. What is recovery? Recovery means this generic name refers to a process resulting in a reduction of flow stress. So the reduction of flow stress, the flow stress is coming down. So what? Why does it comes down? Because the dislocation annihilation. What is dislocation annihilation? Annihilation, we have already seen what is dislocation annihilation. A positive and negative edge dislocation glide in a same plane, which is coming in opposite direction, will form a perfect crystal. That also we have shown in the dislocation dynamics. So this process is a dislocation annihilation. So when the activities starts with this dislocation annihilation, then what do you expect? The total number of dislocation density will, total number of dislocations will come down. As a result, the density of dislocation itself will be decreasing as you proceed. Okay, that's important aspect. And secondly, the rearrangement of dislocation into lower energy configurations. That means all the energy, like see one example already. We have just seen that how a dislocation will try to align themselves in, especially a edge dislocation of a similar sign will align one over the other because of the stress fields, right? We have clearly shown how it if it is more than 45 degree or less than 45 degree orientation, all we have seen. So it forms a low angle grain boundary. That means that is a classical example of a low energy configuration. Right? So like that, so many configurations are possible. One of the primary is the cell dislocation cell. It will form a group of cells. Okay, that is also a low energy configuration. So it could form veins of a string, a dislocation wall, cell. All these things are descriptors of low energy configuration of dislocation. So this low energy configurations will form, and then as a result a subgrain boundaries will form. So when I say low angle grain boundary, that is also considered as a subgrain boundary. So what recovery means is it consists of too many activities which eventually reduces the defect density inside the system and reduce the energy of the system to the lower range, right? So these are all recovery. When you say dynamic recovery, all these activities are expected to operate in a continuous fashion as the deformation proceeds. It is happening continuously. It is not non-stop. That is why it is dynamic. Okay. So we are talking about a room temperature deformation right now. The same thing can happen at high temperature. That means you can imagine that thermally activated process also will contribute to this dislocation dynamics. Then there again we will talk about dynamic recovery. Okay, so the recovery means these are all the activities, and the dynamic recovery means it acts simultaneously as the deformation proceeds to at the very higher stresses. So what I am trying to convey through this slide is this is the first step we are seeing in a deformation of a single crystals. What are all the microstructural events that is going to happen in a very, very localized scale. In terms of dislocations, we are able to categorize them or describe them. What are all the activities? And then basically what we are trying to explain, we are trying to explain the stress response. Okay, the stress response of a single crystal. Okay, how it behaves and why it behaves, and what is the consequence of this deformation and so on. Okay, so this is very basic and fundamental. These ideas should remain intact in our mind so that we can relate this with the other crystal systems. So already we are comparing this FCC with the BCC, and BCC we are not going to see this kind of well-defined stage behavior. Rather, it is a full stress strain curve is going to be similar to what is shown in the stage 3. That means the very beginning of the deformation itself will involve all the activities, the dislocation activities or recovery activities what we are seeing in the stage 3 in the BCC. That is how we should start, at least we should start thinking in those directions, and then we will get matured as we proceed, and then the understanding will improve once we start from here. Okay. So the two major processes by which recovery occurs are cross slip and a dislocation climb. So that we also have seen what is climb, dislocation climb, right? In a dislocation, how it moves up. It can move up or it can move down depending upon the circumstances. So the recovery by itself can take place by two primary mechanisms called cross slip and dislocation climb. Next comes the important another mechanism called twinning. What is twinning? Okay, a crystal is said to be twinned when one portion of its lattice is a mirror image of the other. Okay, the crystallographic plane of reflection is known as the twin plane. So you look at this image. This is a crystal lattice of a cubic system, and this is 110 plane, and what you are seeing here is a twin region which shows a twin plane 111 and then the twin direction 112, and then you can see this atom displacement is proportional to the from where the twin plane starts, right? It's actually increasing from here. The displacement increasing as you move from twin plane. Okay, so this is a twin region, and this is a kind of a mirror image of this, and here is the mirror image of this lattice. So this is, I will give much more description of this in the next slide. Okay. Twins may be formed during the growth of the crystal or may be produced by mechanical twinning, which occurs by a homogeneous shear of successive planes of atoms by amount of the twinning vector parallel to the twin plane. Twin planes, vectors and the shear produced are given in table for FCC, BCC and HCP crystals. Okay, what are this? So like a slip system, we have a twin system, you can say that. So twin plane and direction in FCC 111 and 112 direction. This is a kind of amount of shear it can produce. You can measure the shear. This is 0.707. Okay. In BCC it is a reverse 111, 112 planes and 111 direction, and it also will produce a shear of equivalent to what is being produced in FCC. But in HCP, it is 10 bar 12 and the direction is 10 bar 1 bar 1. Examples are cadmium, zinc, magnesium, titanium, beryllium, and then you can see that the amount of twinning shear produced by these crystal systems or materials are significantly low compared to FCC and BCC. But it is not that simple here. I will just first describe this a little more for your understanding, then we will move on to the next idea. So what is the same thing? Cubic 110 plane is shown here, and this is a twin plane, and this is the polished surface. So this plane is oriented little with an angle with the surface, and then this is the shear force which is acting on this system, and this 110 plane is it's on the plane of screen here, and the twin plane is perpendicular to this plane of the screen, and this is what the description for this. And then if you look at this twinned region, now you see that since the twin plane is perpendicular to the plane of the screen, computer screen, you can now see that this twinned region also must be an offset. I mean, you can say that it would have come out of the screen, right? If you look at reality, it should have, this twinned region should have come out of this plane of the screen, computer screen, and then it also has created a huge step on the above the polished surface. So these descriptions will help you to imagine three-dimensionally how this twins takes place. Okay, so now let us assume this polished surface is a plane AA, and this is a twin plane, which is again, this twin region has come out of this screen, and then there are three circles. One is open circle, and a circle with a dashed line, and the circle with a solid, completely filled circle. Okay, so the open circle is untwinned lattice. The circle with the dashed line is the original position of the lattice point before it twinned. So you can see that the displacement of the atom, you can see from here to here and here, it is proportional to the distance between distance from the twin plane. So you can see that it is the displacement here is small, slightly increased and slightly increased, and like that. So it is proportional to the twin plane distance. Basically, you can just understand like that, so that it is easy to visualize. And another important point is, suppose after it is a kind of a surface relief, you can say. See, this is a polished surface. That means this twin has created a step. So it's a kind of a relief, surface relief. So literally, you can polish this, and then you can remove this. By polishing, it will get removed. But still, you will see the twin, because this orientation, okay, the twinned orientation, since it has come out of this plane of the screen, it is completely different orientation as compared to the untwinned region. So even if you remove this portion above the polishing surface by polishing, after etching you will be still able to see this twinned region because of the different orientation. So in a polished surface, and by etching, you will be able to visualize the twins. So these are all some of the very basic idea about the twinning. So what are the technical aspects? Let us now look at them a little more closely. The twinning can happen by two ways. One is by annealing, another is by deformation. So the one which we are now looking at is mechanical twinning, is by the shear force, right? So the mechanical twinning differs from the slip. So now, since we are talking about deformation mechanisms, we are comparing twinning versus slip. Okay, the twinned portion of the grain is a mirror image of the original lattice, whereas the slip portion of the grain has the same orientation as the original grain. Very important point. Okay, just now I demonstrated to you how this orientation is going to help, because even by etching you can see it. Okay. Slip consists of a shear displacement of an entire block of the crystal, whereas the twinning is a uniform shear strain. Please understand this. This is very uniform shear strain. You look at the whole deformed region, a twinned region. It's a cooperative movement of many atoms. Okay, but not to the extent of the slip vector, but it is only a fraction of that slip vector or inter atomic spacing. Okay, that we will see. The direction of the slip may be either positive or negative, while the direction of the shear in twinning is limited to that which produces the twin image. So that it is clear now. Very important point is the stress required to produce twinning tends to be higher and less sensitive to temperature than that necessary for the slip. Very, very important point. The stress required to produce a twinning is higher. Okay. It is still uncertain whether there is a critical resolved shear stress for twinning. Another important point. When we are comparing two mechanisms, slip and twinning, about slip we talked too many things and it was very clear. We established the mechanisms and how it takes place, shear plane establishment. We looked at octahedral planes, and then critical resolved shear stress. Also, we have seen that it is a characteristic of a material. So everything is clear. But here, still we don't know whether there is a critical resolved shear stress for twinning. The stress required to propagate twinning is appreciably less than that required to initiate it. Okay. Mechanical twinning usually occurs when the applied stress is high as a result of strain hardening or low temperatures, or in HCP metals when the resolved shear stress on the basal plane is low. So this is a very fundamental idea and important idea, because you cannot just like that form a twin. It requires some conditions. What are the conditions? Applied stress need to be at higher side as a result of strain hardening. Okay. Or at low temperature. So either it should be temperature effect or the stress effect, or the crystal system itself. If it is a very different crystal system like HCP, where the number of slip systems available for slip is limited. It's only basal slip, right? And it's not like an FCC where you have a large number of high density planes, right? They are not here in HCP. Thus, a thin lamellar twins called Naumann bands may form in the iron loaded rapidly at very low temperatures. This is one example how this forms. Since slip can occur only on the basal plane in many of these metals, twinning can both contribute to the bulk deformation itself and an important reorient the lattice more favorably for the basal slip. So this is again now we are trying to describe the deformation in the HCP kind of systems where the number of slip systems or favorable slip systems are limited. Twinning is believed to occur by a dislocation mechanism. Okay. Although twinning dislocations have not been identified experimentally, such a process would differ from that for a slip in two ways. The Burgers vector of a twinning dislocation does not produce a unit lattice translation, and this would not bring a lattice back in register. So this point is a very valid point, and this is how we have been describing the slip, because the moment the slip takes place and the lattice will experience a unit lattice translation by a lattice translation vector. Okay, the translation is by means of a lattice translation vector, but this is not going to happen while twinning. Okay, each plane above the twin plane is displaced by a single twin vector. In the mechanisms proposed for twinning in FCC and BCC crystals, the twinning dislocation is one part of the dissociated slip dislocation, which can spiral upwards over successive planes when pinned at a screw dislocation normal to the slip plane. So this is a kind of a hypothesis how twin can get generated. Okay. The source of this twinning dislocation is most easily visualized in an FCC crystal, for the slip and the twin planes are both 1-1-1 planes. This is one advantage in FCC, because here we see that both twin systems and slip systems, we have seen that 111 planes are going to be the primary planes. So what people believed is, if you look at this octahedral plane, the slip vector is a by 2 1 0 bar 1 can dissociate into a by 6 1 1 2 bar and a by 6 2 1 bar 1 bar. Okay. So this particular slip vector can cause the or can be a twin vector in an FCC. This is one hypothesis. To identify the origin of the twinning, this is one kind of hypothesis. A slip dissociation of a type A by 2 1 0 bar 1 dissociates into two partial dislocations. So that's what's shown here. And A by 6 2 bar 1 partial, which remains on the slip plane, and an A by 6 1 1 bar 2 dissociation or a dislocation, which can produce twinning. So this is a slip vector or a slip vector. Here it is a twin vector. It can be a twin vector in FCC crystal, which can produce or can cause a twin. Okay. So what I'm trying to say is, though it is not well established the origin of dislocation activity in twinning, so some of the hypothesis is available based on the experimental observations. Okay, some hypothesis. Okay, we will stop here. We will continue this discussion in the next lecture. Okay, thank you.